Okay, so hello and welcome to this lecture on problem solving sessions. Today we will be solving some questions on decision trees, clustering algorithms, and support vector machines. The set of 5 questions will help you to learn more about these concepts and to know more about machine learning in general. And these are important questions as part of the GATE exam. As always, my name is Aditya Agrawal and I am a MS graduate in computer science from IIT Madras. I was an ex-data scientist at High Radius Technologies, Hyderabad, and I hold a BTech in computer science from KIT University. So moving on, let's look at the first question. What is the purpose of pruning in decision trees? Option A is to reduce the depth of the tree and prevent overfitting. Option B is to optimize the tree's parameters. Option C is to handle missing data. Or option D is to improve the tree's interpretability. So the correct answer to this question is option A. Now, why is A the answer? So first you have to understand what is pruning. So I hope you all understand what is a decision tree. So decision tree typically involves a feature, let's call it F1. You divide your set of data points, let's say if it is greater than some threshold or less than threshold, then over here you use some other feature to break it down further. And if you keep on going like this, what you might think is at the end of the tree, everything is a pure node. What do I mean by pure node? All the data samples that are present in the leaf nodes, they belong to only one level. Either it is, let's say there are two classes. Let's say there are two classes. It's a binary classification problem. So either it will be 0 or 1, right? That is what you are assuming. But here what happens is if you keep on training your model and keep on trying to do this way, by which you are trying to keep on increasing, keep on making each node pure, then it might so happen that you will also try to now fit the noise to the data. For example, if there is a single data point x1 that has a feature that has a class 0, let's say, okay, it's an example, then you will try to fit your model for x1 as well, right? So you are also trying to fit the noise in the data. In the sense, you're trying to overfit your data. You're trying to fit more than it's necessary. So what you can do is you can prune your tree. You can say, hey, maybe f2, if it is less than equal to some threshold t1, then you do not have to break it further. You can say that class 0 occurs in 5 instances, class 1 occurs in 11 instances. And then you can say that over here, the probability of class 1 is 11 by 16, right? Which is more than the probability of class 0. So at this point here, you are trying to make an assumption to the data. You are not, it's not a pure node, right? It's a mixture of the two classes. It's not a pure node. It's an impure node in the sense two data points are both the data points, and all the data points in this node are either 0 or 1. They are not a particular class. They do not belong to only a particular class. So this is the way by which you can say that, hey, if you reach here, I can't say with certainty, but with a probability of 11 by 16, that your class is 1. Okay. And then you can have some threshold and to decide more than 0.5, you can call it 1, or more than 0.6. It depends on the threshold that you set and the problem at hand. So, but this is what. So you will have, so pruning means you're trying to cut the tree. Cut the tree. Pruning means to cut, right? You're trying to stop the tree from building beyond a certain point. In the sense, you're trying to reduce the depth of the tree and also trying to prevent the overfitting. So option B doesn't make any sense, to optimize the tree's parameters. I don't know what parameter you're trying to optimize here. Some people might argue that I had used something called as scikit-learn, and there is a parameter called max depth, which controls the maximum depth of the tree. You can set that to 1, that way you are optimizing it. Maybe, but that's not the correct way to say it's optimizing it. You're just setting a value something else that you will only train till particular depth, right? So, and to handle missing data, Option C says that is also not quite correct, because if you have a missing data, then how will you even break it in the function one, right? So, and also to improve the tree's interpretability, again, there's nothing. If you have a smaller tree, it will be easier to read, but that won't actually improve the tree's interpretability, right? So, option D is also not the correct answer. So, moving on to the next question. Consider the two statements. Statement 1 says, in a decision tree, the leaf nodes represent the class label or the value to be predicted, and the decision trees are prone to overfitting. Which of the following statements is true? Only S1, only S2, both S1 and S2, neither S1 nor S2. So we just saw in the previous question that S2 is true because decision trees are actually prone to overfitting. Statement 1 says, if we have a decision tree, the leaf nodes represent the class label or the value to be predicted. Sometimes there is also regression models that you can design. So decision tree regressor, random forest regressor is there, which is bagging, that's not in your syllabus. But the leaf nodes represent the class label in a decision tree. Is it true or false, right? Again, you might be confused here if you read the previous if you saw the previous question where I was talking about pruning and an impure and a pure node. Unless and until it is not mentioned anything here that you are doing pruning or anything, consider everything as a pure node, which means that all the leaf nodes of the tree will contain either 0 or 1. Let's say there's a binary classification problem. Y belongs to either 0 or 1, right? All the leaf nodes will contain data points that have a class label of either 0 or 1. So in a decision tree, the leaf nodes represent the class label or the value to be predicted. So S1 is actually correct, S2 is also correct. So actually both S1 and S2 are correct. Okay, fine. Let's go on to the next question. In this one, K means clustering. In K means clustering, what is the purpose of the elbow method? So if you remember the elbow method, what does it do, right? So if you see, if I draw the graph, right? So this denotes some value K, and here denotes the within cluster sum of squares, and elbow method is something like this, right? Right? It's something not a straight line actually, but it is something like this, right? So at this point, maybe you can say that this is the optimal value of K. Now, what is the value of K? K denotes the number of clusters that you select. And to find out the number of clusters, that is K, is a hyperparameter, right? And in case you don't know what is a hyperparameter is a parameter that you set before executing your model. Before you try to train the model, you use some set of parameters which are called your hyperparameters. These parameters are not trained by the model. These parameters are used to train the model. Okay. For example, the K-means clustering algorithm, there is no way you can train K. You are trying to fit a cluster, right? You fix the value of K before actually training the model. So there's if I tell you to find out the optimal value of K, which is the value of K that you want to uh, find, such that your within cluster sum of squares is the minimum. So for that case, what you will do is you will draw something called an elbow method, which is if you consider different values of K and plot the graph according to this. So plot the graph where the x-axis denotes the K number of clusters and the y-axis the within cluster sum of square. It starts at a very huge value. The value of K is 1. It starts at a huge value, and as you increase the value of K, it reduces. It kind of goes flat at this point. So you have to find out where you can find the optimal value of K, and that will be your answer. Because why we do this? Because K means clustering. The more the value of K, the more this the model complexity increases too much, right? You're trying to find out so if you have, let's say, K equal to 10, for instance, then you have 10 cluster centroids, and you are trying to you're trying to calculate the distance of each data point to all the 10 centroids, and then trying to find out which data point falls closest to which centroid, and that will be a pain. So that will increase the complexity of the models. You have to also have to take care of that, and that is why we use the elbow method to find out which value of k will give us optimal result. Optimal result in the sense can give us the good the minimal within cluster. I'm saying minimal, not minimum. Okay, minimal within cluster sum of squares, keeping in mind to not mess with the model complexity. So that is why K-means clustering. The purpose of the elbow method is to determine the optimal number of clusters. The other options, option B says to identify the best distance metric. Doesn't make any sense. We are not talking about distance at all here. Distance metric we used once we fix the value of k, then we try to find out that for using that k, we use a distance metric that calculates the distance from a point to the cluster centroids. And then option C says to select the best initialization method. That is also not true. You're not actually initializing it. We are trying to run this and then trying to find out the value of k that you can use to train your final model. And option D says to determine the convergence criteria is again untrue. There is no talk about convergence criteria in this entire discussion on elbow method. So the option A is the correct answer. Moving on to the next question. Consider the following statements. S1 says it is not necessary to have a dependent variable for applying dimensionality reduction algorithms. Statement S2 says dimensionality reduction algorithms are one of the possible ways to reduce the computation time required to build a model. So this question is on dimensionality reduction, PCA, LDA. LDA, I know I have not taught you because it's a very broad topic, and since it was a crash course, so knowing about LDA in the current scenario would be not a pleasant experience. It won't be very helpful for you. So that's why I'm not taught. But LDA typically takes in the target variable into account because PC only considers the independent variables, the input features. It does not consider the target variable, dependent variable. LDA also considers the dependent variable. So statement S1 says it is not necessary to have a dependent variable for applying dimensional reduction algorithms. S1 is true in the sense you actually it's not necessary to have. If you are, let's say, if you don't have a dependent variable, for example, if you are considered a unsupervised learning algorithm and you want to reduce the dimensions, can't you do that? Obviously you can do that. You can use PCA to do that. But if you say I don't have a dependent variable but I want to do linear discriminant analysis or LDA, that is not possible because the LDA or linear discriminant analysis expects that it takes into account the target variable as well. So statement S1 is it is not necessary to have a dependent variable for applying dimensional reduction algorithm is absolutely correct. It is necessary to have a dependent variable only if you are trying to use linear discriminant analysis. It is not necessary to always have a dependent variable. If you are using PCA, it doesn't make any sense. It won't even take into account. Statement S2 says dimensionality reduction algorithms are one of the possible ways to reduce the computation time required to build a model. Yeah, so that is one of the primary reasons why you use dimensionality reduction, where if you have a, let's say, n feature set, you use some algorithm like PCA or LDA, right, to find a subset of small n features, right, where your value of n is less than or equal to capital N, right? So you try to reduce the dimensionality of the data using PC or LDA, by which you will have reduced number of features, and that can help you, that can reduce the computation time required to build the model as well as train the model. Build the model, train the model, the same thing in the sense, and the model complexity is also much more reduced in this scenario. So that is why option C is correct in the sense both S1 and S2 are actually correct. Okay, hope you understand. Let me repeat once again so that you get it. So statement S1 was saying it is not necessary to have a dependent variable. Again, try to understand what it tries to say. It is not necessary to have a so if I tell you you want to do PCA, okay, and I tell you this is a dependent variable, you will tell me, hey Aditya, I don't need a dependent variable to do PCA. So, but yeah, if I was doing LDA, then I may be using, maybe would need it. So it is not necessary to have a dependent variable for applying dimensional reduction algorithm is correct. And S2 says that dimensional reduction is one of the possible ways to reduce the computation time. So when you're trying to build a model, let's say you're trying to build a KNN model, naive Bayes model, right? So if you remember naive Bayes, then naive Bayes had something like this: Py equal to x is directly proportional to P of x given y multiplied by P of y. So the probability of observing a class y given the feature vector x is directly proportional to the probability of seeing that feature vector x given that class y multiplied by the probability of y. And then you typically write this like product of I equal to 1 to n, right? Maybe this can be capital N because I was using the same convention before. P of xi given y multiplied by P of y. So you can see that for each particular feature from x1 till x capital N, you are trying to find the probability of x of I given that feature y, given that label y, and then you are taking the product of all of them. So this if you can reduce it to little n, then your will be number of product terms will become lesser 9, right? So in this case, it will become lesser, and your computation time for the model will be much more reduced. Okay. Okay, so you can form an example using other scenarios as well. You can also do for linear regression as well. You calculate W transpose X, right? So if your feature vector X is reduced, then your W transpose X will be much more faster to compute, right? So you can find out your own examples now, but I hope you get what I wanted to say. The last question for this lecture and this topic is something called kernel SVM. Okay, so maybe I've not talked about this, so let me talk now. The question is, what is the purpose of the kernel trick of SVM? Option A is to transfer the problem from a nonlinear to a linear, to transfer the problem from a regression to classification, to transform the data from non-linearly separable to linearly separable, to transfer the problem from the supervised to unsupervised learning. So first, let me tell you what it is, right? What is kernel trick and all that, and then you will only tell me the answer, okay? So consider a very simple case, okay? So let's take this as the, okay, maybe this pen doesn't work today. Okay, yeah, it works. So let's consider this example, right? So this is the x-axis and the y-axis. Let's say there are two classes, green and red. Okay. Oops, sorry. Okay, ignore guys. Wait, maybe I can. Yeah, okay, good. So, okay, maybe it is. Okay, fine. So what I'm trying to say here is, okay, now it shouldn't work. Now it should be fine. Yeah. So let's say there are two classes, green and red. Let's say there are some data points which are in the only x space. Okay. Only x axis. This is the x axis. Okay. This is the x axis and this is the y axis. And let's say there are only data points in the x axis space. Okay. So let me not write this as y. Let me write them as x1 and x2. That will be a bit more easier to learn. So let's say I have data points like this is one, right? So this is green. Okay. I have data point 2, which is also green. Okay. I have data point 3. Maybe I don't have a data point 3. I have data point 4, which is red. Okay. I have data point 8, which is also red. I have a data point, let's say 6. Let's say this is 6, which is green. Okay. 3, 4, and 8. If I ask you if this, can you draw an SVM for this set of data points? Can you find a line that separates these two classes? You might say, hey, this is not possible, right? You can't actually see this, right? This is not possible. What I will do now is, I will say, instead of just one feature x1, So instead of having one feature x1, let me change this data set to have two features x1 and x1 square. Okay. So what would happen is my 1 stays as 1. Okay. So let's say this x1 square feature I denoted by x2. So this is 1, 2, 3, 4, 5, 6, dot, 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 dot. Okay. Let's say this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, and dot. So, okay. So my value that is labeled 1 is now 1 comma 1. So it comes to here, right? 2 becomes 2 comma 4, right? 4 becomes 4 comma 16, which falls somewhere around here. Let's say around here, okay, on the top. Okay. So this is my 4 comma 16. This 6 comma 36 again. Oh, sorry, I need to bring this down because 6 comma 36, 8 comma 64 will be an issue. So 6 comma 34 comma 16. Sorry, it will be 4 comma 16, right? 4 comma 16 falls here. 8 comma 64, let's say, falls here, right? And 6 comma 36, let's say, falls somewhere. It should be in the middle, right? Huh. Now tell me, is this two linearly separable? Right? So if you look carefully, again, this should be a bit more up. You can say that I can draw a line something like this. So I can draw a line something like this. Okay, again, this should have been a bit above. So I'm just drawing it from here, but this should have been a bit above. Okay, this is a line only. So as you can see now, what happened is my data became linearly separable. I hope you can visualize it because why it happened? Because my 8 square was much bigger. So let's say for example, again, maybe you guys are not convinced yet, so that's why I'm doing it. Let's say this was 10 or this was 12. Okay, uh, 1 second. Yeah, this was 12. So 12 square is 144. So it will blow up. It will be out of the screen, right? Out of the page. So now, if you can see, if I draw this line, right? And let's say these are my support vectors. Then the 12 square, which is 144, which is somewhere on the top, let's say it is here, let's say, right? Let's say it is here, correct? So this way now your model, the key thing to learn here is now it becomes linearly separable just by squaring it. I didn't introduce any new feature. I just took the square of x1 and called it my new feature x2. That made my data now linearly separable. And this is called the kernel trick. This is called the kernel trick. So sometimes if you have a there are other examples of this type of data sets as well. So that is something called the kernel trick. Okay, again, the math behind it, I'm not going to talk about it as this was a crash course and you have maybe 10 days to the exam for now, 10 or 9 days. So it's no point. But if you join my classes, then sure, I will teach you this if you have time. But for instance, the thing is to know the concept about why the heck do we even use it, right? So, just a second. I don't know why. I don't know whether you guys can see it or not, but for me, it zoomed in a bit more. Yeah, okay, fine. I'm back. So, what I'm trying to say here is first option says, what is the purpose to transform the problem from a non-linear to a linear? You are actually doing the reverse, right? It was linear, you made it non-linear now, okay? Or maybe you're trying to fit it on a bigger dimensional space such that you get a linearly separable hyperplane. So this is option A is absolutely incorrect. Option B says to transfer the problem from regression to doesn't make any sense actually, doesn't any sense at all. Option C says to transform the data from a non-linearly separable to linearly separable is the correct answer. And option D says to transform the problem from supervised to unsupervised. Again, doesn't make any sense, guys, because you are not doing anything to the individual classes, you are still considering it, right? So option C will be the right answer, which is you do the kernel tree. Again, there are many types of kernels available. There are Gaussian kernels as well. You can explore that if you have time. If you have learned all these concepts, please also go through this. Okay, I'm not saying this is not important, or this is important, because you never know what will be asked in the exam. But basic funda of why we use kernelization is something like we want to convert a data from a non-linearly separable to linearly separable data set. Okay, fine. So what I will do is I will conclude today's lecture with the set of video with today's video where we discussed on support vector machines, dimensionality reduction, and we talked about clustering algorithms, decision tree, dimensionality reduction, sorry, not algorithms, clustering, decision tree, and support vector machines. These lectures are added lectures on top of what you have been taught. So make sure you are also able to understand the answers to these questions so that you can ace the exam. Okay, you can know the concepts told in the exam a bit more. Okay, and feel free to comment down below if you have any questions. If you want to check out our website, go to www.iitiansgateclasses.com. You can mail us at info@iitiansgateclasses.com. You can call us on 974050164. The number is given in the slide here. To know more, if you want to enroll in our course on data science or CS or any other great subject, make sure to check out the website or call us in the number given here. So with this, I would like to conclude this lecture, what I taught today. Hope it was helpful for you guys, and all the best for the exam. Thank you for joining.